Okay, good afternoon, everybody. We're going to get started now. Um, I'm going to pick up where we left off in class, which, if you recall, we were talking about how to find limits. And we were looking for a better way than to just have to graph the function every time and look at the graph. So um, we said that there are certain properties of limits that will allow us to break apart functions into small pieces and deal with them that way. And for example, if you have the sum or difference of two functions, then you know that you're going to be able to take the sum or difference of their limits to find the overall limit. Or if you have a number multiplied by a function like c times f of x, then you can pull the c out front of the limit, take the limit of the function, and then multiply that answer times c. You can break apart products, quotients. You can take the limit of a function raised to a power is the limit of the function, and then that value raised to the power as long as the power is a positive integer. And if you have the nth root of a function, you can take the limit by taking the limit of the function and then taking the root of that, if assuming that root exists. So of course, if the limit turns out to be negative and you have an even root, then that's not going to work. But otherwise, it will work. And we said that the limit as x approaches a of a constant value c is just going to be that constant value. So as an example, if we have the limit as x approaches 2 of 5, we said that's just going to be 5. And we said that if we have the limit as x approaches 2 of x, you just plug in the 2, so that's just going to be 2. So then I said, well, what if I wanted to take the limit as x approaches 2 of 5 plus x? Well, we can break that apart. It's a sum, so we can take the limit of each piece. And we just found the limit of each piece, so that's going to be 5 plus 2, or 7. Okay, so that's where we kind of left off the last time. And now let's continue with this lecture. I'm going to make the screen a little bit bigger. I'm going to move my chat off to the side here. Feel free to ask questions or interject using the live chat box over here. And also tell me if you're experiencing any technical problems. Some of them are on your end. I won't be able to fix them, but other students might have a suggestion, and some of them will be on my end. So, all right, let's zoom out a bit. So the next thing that we're going to look at is there are 3 methods or approaches that we use when we're trying to find the limit of a function that we're given algebraically as a formula. So we're going to look at this example where you determine the limit just by substituting the value into the function. That's right, Taylor, we're continuing section 2.1 right now. We have a little bit to finish up before we go on to 2.2 and 2.3. Okay, so because of those properties that we just saw, you could break this number 1 that says the limit as x goes to -1 of the square root of 2x squared plus 3. You could break it down where you have the square root of the limit, and then as x goes to -1, and then inside that you have 2x squared plus 3, and then you could break that down and you would have the square root of the limit as x goes to -1 of 2x squared plus the limit as x goes to -1 of 3. And then you could break that down even more and break apart this product and so on. But truthfully, what it comes down to is, as long as when you plug in this number, -1, as long as you get a number that makes sense, that's the answer. So we're not going to overcomplicate it here. What we're going to do is just try plugging in the -1 to the algebraic expression. And if it works, if it's defined with a real value, then that's our answer. So we're going to do the limit. We're going to actually, I'm not even going to write limit anymore. I'm just going to write square root of 2 times -1 squared plus 3. Okay, and so, by the way, if your screen looks a little blurry, then on the settings, on the little wheel symbol, you're going to select 360p, and it should clear up a little bit. All right, so we have 2 times -1 squared plus 3 is going to be the square root of 2 plus 3, which is going to be the square root of 5. Okay, so it did turn out to be a real number. It's irrational, but that's okay. So that is what the limit is equal to. Okay, and the only reason we're able to do that is because we have a function that involves roots, and it involves products, and it involves sums, and we know these properties for limits tell us that we can just go ahead and plug in as long as we're going to get a real answer. Okay, so that's the first scenario. Let's look at this item number 2 here. So this is a piecewise defined function. And so if we're, by the way, this value, the 2, this is what I call a boundary value. It's the boundary between where the function follows the rule x squared plus 1 and where we stop and we start following a different rule, x minus 1. I'm going to zoom in. It looks a little small. Okay, so notice that we are being asked about the limit as x approaches exactly that boundary value. X is going to 2. In part A, we're talking about the limit as x approaches 2 from the left. In part B, the limit as x approaches 2 from the right. And in part C, the overall limit as x approaches 2. And then in part D, we're being asked to find the function value at 2. There's a whole bunch of questions about this boundary value. That's because interesting things tend to happen at those boundary values. All right, I'm going to draw a picture of this in a minute to help you visualize it. But I want you to be able to calculate it without drawing the picture because that takes time. So what we want to think about is for part A, remember this is talking about when we have that negative symbol, we're coming in from the left. So what that refers to is if you have a number line of x values, here's the number 2 coming in from the left of 2, we're talking about x values that are less than 2. So when we're coming in from the left, our function observes the rule that whatever x value you have, you plug it into x squared plus 1. Okay, so coming in from the left, we don't actually reach 2, but there would be an open dot on our graph, and everything up until 2 on the left is following this rule. So what we're going to do is we're actually going to plug 2 into this rule as if it were actually part of the domain, which it's not, but if it were, what value would we end up at? So we would get 2 squared plus 1 is 4 plus 1 is 5. So coming in from the left, the function is headed toward the value 5. Coming in from the right, we're talking about x values that are to the right of 2 are bigger than 2. So we're talking about the interval of values where x is greater than 2. For all of those values, our function fits this rule, x minus 1. So even though we don't have an x greater than or equal to 2, it goes right up until that point, and there would be an open dot on our graph. So we are saying that this would, if we could plug 2 in, this would end up at 2 minus 1 equals 1. So we are headed toward the value 1. We don't ever actually reach it because notice that there is no value given for x equals 2. The function is actually undefined. So actually I'm going to write that over here. The function is undefined at 2. Okay, so it was headed towards 5 from the left. It was headed towards 1 from the right. And then now we want to know what the limit as x approaches 2 is. But remember, in order for the limit to exist, the limit from the left and the limit from the right have to be the same, and they're not. So we would say dne does not exist. Now, the reason we were able to plug the 2 in here and here is, again, because x squared plus 1 is a sum, involves a sum and a product. How do we know that the function is undefined at x equals 2? Because we are, it's not included in our domain. This function has what's called a restricted domain. It includes all the values less than 2, and it includes all the values greater than 2, but it does not include the value 2 itself. So no one has defined for us what y value goes with x. So that means there isn't one. So that means it's undefined at x equals 2. I hope that helps, Taylor. That's a good question. So if there had been an or equal to on one of these inequalities, it would have been defined, but it's not, so it's not defined. That's right. If there had been an equal sign, it could be defined, but that would have to have been given to us. And so this function, as it's given to us, it has no definition of what y value goes with that x value 2. So we just say undefined. Okay? All right, so that's how you find the limit algebraically when you have a piecewise defined function and you're trying to find the limit as x approaches the boundary value here. I just want to show you real quickly what that graph would have looked like. Let me pull up Desmos.com has a nice grapher. Let me go. Computer might be a little too overworked at the moment. Let's see if it'll work. Oh, it's taking too long. Let's close that. Okay, so let me just show you. So notice that in item number 2, we had part of the function to the left of 2 look like the graph of x squared plus 1. That's a parabola. So I'm just going to draw, a quick sketch here. So a parabola looks like x squared plus 1 is a parabola that starts at 0, 1. And so it would look like this. And it would go up to, at the x value 2, it actually would have had a value of 5. 2 squared plus 1 is 5. but instead we have an open dot there because there's no or equal to. And then to the right of 2, this is going to look like the graph of x minus 1. So at 2, it would have had a point at 2, 1, but there's not because there's no or equal to. And then it's just going to be a line going up this way. So this is a piecewise defined function. It looks like a parabola on the left and a line on the right. So visually then, if you had this graph, would our results agree with what we found over here? And the answer is yes, because you would follow to find the limit from the left going in towards 2. You'd look at this open dot and say, okay, it's headed toward the y value 5. And then to find the limit from the right, coming in towards 2, we would look at this open dot and we'd say, okay, it was headed toward the y value of 1. And then the overall limit doesn't exist because these two don't match up. And then you can also see on the graph here that the function has no y value on at 2. So the function is undefined at 2. Okay. Let's look at another example. Okay, so for this one, again, you can always just plug in when you have quotients, products, and sums. So any polynomial or rational function, unless, oh, Taylor asked me, how did you make the ray on 2, 1? So back to this graph up here, 2, 1. I know that the formula y equals x minus 1 is a line. It's a line that would be continuing, but we're only using the portion of the line greater than 2. So it's going off into the right here, this portion over here. Okay, so this line segment, this ray that's coming off of the point 2, 1, I didn't draw a precise graph, but if you wanted to, you could just plot some points. For example, if x were 3, 3 minus 1 would be 2. So this would go through the point 3, 2. And you could plot a few more points. But it's coming from this second piece of the function f. Did that answer your question, Taylor? Okay. Okay, so let's look at this next one. So for this next one, what you want to do is you're going to try plugging in, but you're going to get 2 squared minus 4 over 2 minus 2. And what's the problem with that? Does anyone know what the problem is? Why I can't just simplify this and get an answer? So in the numerator it would work, right? 4 minus 4, we get 0. But in the denominator we also get 0. And what is 0 divided by 0? That's right, it would be undefined. Division by 0 is undefined. So we don't just say undefined is the limit. This is what's called an indeterminate form. In other words, it doesn't tell us whether the limit exists or the limit doesn't exist. All it tells us is that we have to use a different approach. We can't determine from this information what the limit actually is. So when we encounter a situation like this, particularly with a rational, remember rational just means fraction. with a rational function that when we plug in, we get 0 in the denominator, then what we can do is we can see if we can simplify the expression. So how do we simplify a rational expression like that one? X squared minus 4 over x minus 2. Let's zoom in a little bit here. Anyone have any suggestions on how we could simplify x squared minus 4 over x minus 2? What do you have to do first? You do have to separate it in the sense that you have to factor it, right? And in the numerator here, we have x squared minus 4. What kind of a pattern does that fit? That's right, Greg, we need a factor. And how does x squared minus 4 factor? It's a difference of squares. Very good, Taylor. So what that means is you're going to think of it as x squared minus 2 squared. And a difference of squares factors good into conjugates, x plus 2x minus 2. So this is the limit as x approaches 2 of x plus 2, x minus 2 over x minus 2. All right, so it turns out that if you can simplify algebraically, that you can actually get the same limit. So what I mean by that is the limit as x approaches 2 of this complicated expression is the same as the limit as x approaches 2 of just x plus 2 if you cancel out the x minus 2 and the x minus 2. So you can try simplifying and then plug in again. Now, can we plug into this one successfully? Yes, that's going to be 2 plus 2 equals 4. So it turns out that the limit is 4. Now, why did that happen? Why are we allowed to cancel like that? Well, in fact, this factor of x minus 2 that was causing the 0 in the denominator, the effect it has on the graph is that it just makes a little hole in the graph. So I'm actually going to open a blank page here and show you the graph of x squared minus 4 over x minus 2. So if I were to look at the graph of y equals x squared minus 4 over x minus 2, y is equal to x minus 2, x plus 2 over x minus 2. This is undefined when x is 2, so x is not allowed to equal 2, right? So assume, though, that x is not 2, then these divide out, right? Like let's say this is x is 3, you'd have 1 over 1, or if x is 5, you'd have 3 over 3. This would divide out and leave a 1. So as long as x is not equal to 2, y is just the line x plus 2. So I'm going to graph that line. Oops, let me get my good graph out here. Okay, the graph of x plus 2 is a line that has a y-intercept at 2, 0, 2, and it has a slope of 1. So, and it also goes through, say, 2, 4. Okay, so there's our line. All right, now remember we were talking about, but x is not allowed to actually equal 2. There's an open dot right there at 2, 4. It would have been 4 if it were allowed to equal 2, but it doesn't actually reach 4. So this is a hole in the graph. Now what we were interested in was the limit as x approaches 2 of the original function, x squared minus 4 over x minus 2. And what I'm showing you is that that is exactly equal to the limit as x approaches 2 of the line x plus 2. Because even though this dot isn't filled in, if we come in from the left and the right, we're headed towards that dot. And limits are all about what value, what y value we're approaching, which is 4, not what y value actually occurs. So although this function is a function that looks like a line with a hole in it, and this function, x plus 2, is a line without a hole in it, they have the same limit at that point, which is 4. So the moral of this story is that if you can simplify the rational expression to eliminate the indeterminate form of 0 over 0 and not have that anymore, then you can figure out what the limit is. Now, if it had been a number over 0, this would not apply, because then a number over 0, you can't simplify, you can't cancel out common factors and get that 0 to go away. And so, but a 0 over 0, that potentially can be simplified in this way. Okay, so given the limit as x approaches c of a quotient, f of x over g of x, it has an indeterminate form when f of x is equal to 0 and when g of x is equal to 0, both at the same time. Well, I shouldn't say of x, I should say at c, right? If f of c is 0 and g of c is 0, if we plug in this x value and we get 0 on the top and the bottom, we have an indeterminate form. And so we have to try simplifying to get rid of the indeterminate form. Okay, so let's look at a couple of examples like that. Is everybody still doing all right? Okay, so in part A here we have the limit as x approaches 1 of x minus 1 over x squared minus 1. Let me zoom in a little bit. Okay. All right, so if we were to try to plug in the 1 right now, we would get 1 minus 1 over 1 squared minus 1, which is the indeterminate form 0 over 0. So that doesn't work for us. So we would have to try to simplify the expression before plugging in. Now, when you do this, I'm going to be very picky about how you write this out. Okay, a lot of times people want to drop the limit expression and just start simplifying the algebra part, but it would be untrue to just write this. Okay, the limit of this does not equal the function. The limit equals the limit of the function. So I want to see you write your limit each time. So this is going to be the limit as x approaches 1 of x minus 1 over x squared. I'm sorry, let's factor it. This is the difference of squares, so it's going to factor into x minus 1, x plus 1 in the denominator. Okay, so now we can reduce x minus 1 divided by x minus 1 is equal to 1 as long as x is not 1. Now, you don't have to write x does not equal 1. You don't have to write down that you're making that assumption, because when you're calculating a limit, this notation implies that you're only concerned about what's happening near x, not what's happening at x equals 1. What's happening near x equals 1, I should say, not what's happening at x equals 1. So we do not need to worry about what happens when x is equal to 1. So my point is that you can just write equals the limit as x approaches 1 of 1 over x plus 1. All right, now that we got rid of that factor x minus 1 that was causing a 0 in the denominator, look, now we can plug in the 1. So we have the limit as x goes to 1. Oh, I'm sorry, I don't even need to write that anymore. Once you plug in, don't write the limit anymore. So we're going to have 1 over 1 plus 1, or 1/2. Okay, so if we were to look at the graph, which we're not going to do because that's extra time, but if we were to look at the graph, you would see that coming in from both the left and the right, it's headed toward a y value of 1/2. All right, now we're going to move over to part B here. Remember, you can, if you need me to slow down, repeat anything, just type into the chat bar. All right, so here for part B, we're taking the limit as x goes to 1, again, of x minus 1 quantity squared over x squared minus 1. So this is going to cause an indeterminate form. If we try to plug in, we get 1 minus 1 squared over 1 squared minus 1, which is 0 over 0, an indeterminate form. So we don't know if the limit exists or the limit doesn't exist from that. All right, so what we're going to do is try simplifying algebraically, and when we do it, we're going to write our limit on every step until we plug in again. So in the numerator, we have x minus 1 times x minus 1. You don't have to write it that way. I just want to emphasize that this is a product. And in the denominator, we have that difference of squares again. X minus 1, x plus 1. Oops. Okay, so now we're going to divide out our common factor. As long as x is not 1 at every other x value, this divides out to give you a 1. So we're really looking at the limit as x approaches 1 of x minus 1 over x plus 1. So we try plugging in again. So this time we're going to get 1 minus 1 over 1 plus 1, which is 0 over 2. 0 over any number is just 0, right? It's okay to have 0 in the numerator as long as you don't have it in the denominator. So our limit of this function is 0. So if you were to look at the graph of this function, you'd see that coming in from the left and from the right, you're headed towards a y value of 0. Okay? All right. Okay, so there's two methods that we've discussed. One is just substituting the value into the function to get the limit. You can only do that if it, quote, works, right? And then second is if you get an indeterminate form, you simplify the function and try substituting again. That's method 2. And then we actually already did method 3 earlier in the lesson, which was we used the graph of the function to find the limit. So those are the 3 ways to find the limit. The last topic in section 2.1 that we need to cover is called the difference quotient. The difference quotient is this part right here. It's called the difference quotient because it involves a difference, a subtraction, and it involves division as well. We're not going to go into great detail right at this moment about what this represents, but I will tell you it's just a way of representing a slope in function notation. It's going to be a very important quantity for us. Calculus could have just as easily been called slope. That's how important slope is in the study of calculus. But anyway, what we're going to be doing with this formula is taking the limit of it as h goes to 0. So we are going to need to practice plugging into the difference quotient and evaluating the limit. So we're going to use the difference quotient and a four-step process to find the limit for each function using the given value for a. Won't let me grab it. Okay. So let me write down the formula down here so we can see it on our screen. So this is going to be, we're finding the limit as h goes to 0 of f of a plus h minus f of a all divided by h. Okay, we're just going to focus on the mechanics of doing this calculation before we try and understand what it represents. All right, so they're telling us that f of x is 7 minus 2x and a is 4. H stays a variable. H is the variable that we're finding the limit with respect to. We're going to first rewrite this expression with the 4 instead of the a. So what we're actually finding is the limit as h goes to 0 of f of 4 plus h minus f of 4 all divided by h. Okay, now the first step in this process is going to be to figure out what f of 4 plus h is. The second step is going to be to figure out what f of 4 plus h minus f of 4 is. The third step is going to be to divide that whole thing by h. And the fourth step will be to take the limit. Okay, so how do we find f of 4 plus h? So remember we have a rule for f here. F of x equals 7 minus 2x. And what we're doing is we're plugging in, instead of x, we're plugging in, excuse me, we're plugging in 4 plus h where the x is, right? So the 4 plus h is getting plugged into the function. Okay, so this means that we're going to have 7 minus 2 times 4 plus h. All right, so distributing the negative 2 through the expression, we're going to have 7 minus 8 minus 2h, which simplifies to just negative 1 minus 2h. Okay, so we found f of 4 plus h. So f of 4 plus h, this part, we just found is negative 1 minus 2h. F of 4, we haven't figured out yet, but what would you get if you plugged 4 in for x? So f of 4 is going to be 7 minus 2 times 4, which is going to be negative 1. So we're going to take what we know f of 4 plus h is equal to, which was negative 1 minus 2h. And we're going to subtract from that f of 4, which was just negative 1. Okay, negative 1 minus 2h minus negative 1, or in other words, plus 1, is just going to leave us with the negative 2h. it should be the case, generally speaking, that when you complete this step, you end up with something there where all the terms have h's in them. Any terms that don't will generally cancel out. All right, so now in step 2, what we found was that f of 4 plus h minus f of 4 is negative 2h. But that needs to be divided by h. By the way, in the formula, we're taking a limit as h goes to 0, so we don't care about when h is 0. But just to be clear, this will cancel out as long as h does not equal 0. This is going to be equal to negative 2. All right, step 4 then is going to be the limit as h goes to 0 of all of that turned out to be just negative 2. And when we have a limit of a constant, right, the negative 2 is a constant. It's not changing. There's no variable in it. When we have a limit of a constant, it's just going to be that constant value. So the answer is negative 2. Okay, now remember I told you that the difference quotient represents slope. So if you'll notice, I'm going to shrink this a bit, zoom out. In the problem that we started with, we were looking at the function f of x equals 7 minus 2x, which is a linear function with a slope of negative 2. So it makes sense that if this is truly related to slope, that we ended up with a negative 2. If you calculate the limit of the difference quotient for a linear function, you're always going to end up with the slope there. But of course, we're going to be doing it for lots of other kinds of functions as well. And those will not end up to be an obvious solution. Okay, so that's the end of section 2.1. Now we're going to move on to 2.2. I see a question from Taylor. Will the questions on the homework tell us when we need to use the difference quotient? Yes, in the first homework, you only have to do it if it specifies use to evaluate the difference quotient. Later on in the semester, when we're doing derivatives, which involves a limit of a difference quotient, you will only have to use, we'll have shortcuts and then we'll have the long way. The long way will use the limit of the difference quotient. So in that case, you will only have to use that long way if I tell you to, and otherwise you're allowed to use the shortcuts. Okay, section 2.2 now. Section 2.2, we're talking about infinite limits and limits at infinity, locating vertical asymptotes, and finding horizontal asymptotes. All right, so when we see the word infinity, we're talking about increasing values without bound. In other words, it just keeps increasing forever. At least if it's positive infinity. So our x values say, if they're approaching infinity, if you say x is going towards infinity, that means the x values are getting bigger and bigger. So, you know, you're looking at the x value 1,000,000, or the x value 9,000,000, or the x value 10 billion is even bigger, and we just keep growing and growing and growing. So without ever stopping, that's infinity. Okay, a vertical asymptote is a vertical line on a graph which the function gets very close to but doesn't cross. And a horizontal asymptote is a horizontal line on the graph which the function gets very close to. It is possible that the function crosses a horizontal asymptote in we'll talk about why in a minute. Oop, what just happened? Here we go. Okay. But the reason why we're talking about vertical and horizontal asymptotes in the same section as infinite limits and limits at infinity is that they both involve infinity and limits in some way. So before I write down what the definitions are, let's look at a couple of examples. So in this example, we have this graph on the right, y equals 1 over x squared. And it asks us to analyze the function. HA stands for horizontal asymptote, and VA stands for vertical asymptote. So where do you see a horizontal asymptote on this graph? What would be the equation of the horizontal asymptote? And by the way, you might recall that horizontal lines always are of the form y equal to a number. So in this case, it would be y equals what? So we're looking for a line that's horizontal that the graph of the function gets very, very close to. Good, the horizontal asymptote is y equals 0. So we can see here that the graph is getting very close to 0 at the ends. This is called the end behavior of the graph. It's getting very close to 0. The values would be tiny little fractions, the y values. Okay? How about the vertical asymptote? Remember, vertical lines all have the form x equals something. So what would be the vertical asymptote in this case? Do you see a vertical line that the graph is getting close to? That's right, x equals 0. You see how the function's going up? As it's going up, it's getting closer and closer to the y-axis, which is the line x equals 0. Okay, so now let's find some limits here. These are going to be limits involving infinity. We haven't done that before. And they involve infinity because of these asymptotes. So here, for example, let me zoom in a little bit. Okay. So in part A, we have the limit as x goes to 0 from the left. The limit as x approaches 0 from the left. So remember, we need to look at our graph and we need to look at the x value 0, which is here in the center. And we need to look in a neighborhood around that, close to 0, which I'm just gonna say is like around this area here. Okay, but we're looking on the left, coming in from the left. So coming in from the left would be following along this part of the graph here. So as x gets really close to 0 on our graph, what's happening to these y values? Following along the graph with my finger, I would see that the y values, let's say here, the y value is 1. Here the y value is 2, 3, 4, and it's just going to keep going up, right? So in fact, it's increasing without bound. It never actually touches the x value 0. The function is undefined at 0. You could see that if you plug 0 into 1 over x squared. Okay, but it just keeps increasing, increasing, increasing. The tinier the fraction that we plug in, negative fraction, the larger the result we're going to get for y. So what we say is the limit as x approaches 0 from the left is positive infinity, or you can just write infinity. You don't necessarily have to put the positive symbol there. Hello, Josh. I'm glad you were able to fix the problem. Okay, so now let's look at part B. Part B, we're still looking in the neighborhood of 0. We're still looking near 0, but we're looking on the right side. So we're following with our finger along the graph here, right? And we're seeing what's happening to the y values as the x values get closer to 0 from the right. So you'll see the same thing is happening. The graph is pointing upward, right? So if I pick, say, the x value 1/2, then we're going to get 4. If I pick the x value 1/10, we're going to get 100, and it's just going to keep getting bigger that way. So as we approach 0 from the right, the graph is going upward towards positive infinity. Okay, so notice that these are two limits, one from the left, one from the right, that result in infinity as the answer. Okay, now we're going to look at a different thing, which is limits to infinity. So we're going to ask the question, when x values are going toward infinity, what's happening to the y values? So when we say that, we're talking about plugging in larger and larger x's through 2, 3, 4, 10, a million, right? And what is happening is the function is getting closer and closer and closer to the x-axis, to the line y equals 0. So the y values are approaching 0 on the right side of the graph. They're getting very, very close to 0. Okay, that's what this limit is telling us. This limit discusses what's called the end behavior of the graph on the right. The end behavior of the graph on the right-hand side is the limit as x approaches infinity. Okay? Some graphs have a value like this one that they approach, so a finite value, and some graphs go up, out into space, and their end behavior is out to infinity. All right, looking at this one, this is talking about the end behavior of the function on the left. So on the left here, as x gets to be a bigger and bigger negative number, this graph is still getting very close to 0. So this limit is 0 as well. Anytime a graph settles into where it's very close to a horizontal line, its limit to infinity or negative infinity is going to be a finite value. Okay, let's look at another example. So what would be the horizontal asymptote, the equation of the horizontal asymptote for this function pictured on the right? Anybody have a guess as to the equation of the horizontal asymptote? Taylor got the other two. Can anyone else? Oh, Taylor got it again. Oh, close. Actually, Taylor, you're off just a little bit. It's a good guess, though. -2. Good. Thank you, Marianne. So horizontal asymptote y equals -2. Who can tell me the vertical asymptote? What's the vertical asymptote? Good. X equals -1. Make sure your horizontal asymptote is always a y equals something, and your vertical asymptote is always an x equals something. All right. So each of these limits has something to do with these asymptotes. In fact, The reason we have asymptotes is because we have limits from the left and the right that go to infinity, or limits to infinity that approach a finite value. So, for example, the limit as x approaches -1 from the left. So looking in the neighborhood of -1, here's the -1 x value. Coming in from the left towards that x values, you pick x values closer and closer to -1. What's happening to the y values? Looks like the graph, as it gets closer and closer to this -1, the y values are becoming what you might refer to as larger and larger negative values. What we say is that it's decreasing without bound. It never stops decreasing. That's right, it goes towards -infinity. Very good. So this one is going to be -infinity. Okay, again, that was the limit on the left side of -1. What about the limit on the right side of -1? So the right side of -1 is the other side, the other portion of the graph. We're still getting close to an x value of -1, but we're following with our finger along the piece of the graph on the right. And so what's happening to the y values as we pick x values very close to -1 is that it's increasing without bound. That's supposed to say increasing without bound. In other words, it's going to what? Yes, positive infinity. Very good. Okay, so when you have a vertical asymptote, that's only going to occur when you have a limit from the left to right, which is either increasing or decreasing without bound. That's exactly when that happens. Now, what the limit as x approaches infinity is talking about is the end behavior of the graph, and that's going to result in any horizontal asymptote. That's what causes it to happen, is if the limit happens to be a finite number. So in this case, if we want to go look at the end behavior on the right, we're talking about the limit as x approaches positive infinity. What's happening to the y values as the x values increase without bound? As the x values get larger and larger, what are the y values getting close to? -2. Very good. That's why we have a horizontal asymptote, y equals -2. And if you look as x goes to -infinity, the end behavior on the left is the same in this case. That's not always the case, but it frequently is the case. So this is actually getting very close to -2 when you go to the left as well. Okay, so limits to the left and right that result in positive and negative infinity cause vertical asymptotes. Limits to infinity that equal a constant value, those cause horizontal asymptotes. Okay, what would be the limit? Here's a new graph. What would be the limit as x approaches infinity of h? The limit as x approaches infinity. So again, we're looking at the end behavior on the right. And we're asking ourselves, as the graph goes off to the right, as x values get larger toward positive infinity, is this settling in on a particular y value? Good, -1. You see that horizontal asymptote, -1. Okay, and now how about the end behavior on the left? The end behavior on the left means as the x values approach -infinity, as the graph goes off to the left, and yes, good, it's approaching, it's getting very close to the y value 1, 0.9, 0.999. Okay, what's the limit as x approaches 0 on this graph? So remember, when we are asked to find a limit as x approaches a particular numerical value, you have to look at the graph coming in from the left and from the right, and they have to be headed towards the same value. Good, Karina, that's right. They're from both directions, it's heading towards 0. That one doesn't involve infinity, right? This is more like the ones we did the other day. Okay, so I'm going to scroll back up to the top here, back to our vocabulary words, and I'm just going to make a note that a vertical asymptote is going to occur when you have a limit as x approaches some number c from the left or from the right, it doesn't matter, of the function f of x equal to positive or negative infinity. Then that means you're going to have a vertical asymptote x equals c. And to get a horizontal asymptote, that happens when you have a limit as x approaches positive or negative infinity of f of x, and that turns out to be some number c. Then that means that you have a horizontal asymptote y equals c. Oops. Sorry about that. Okay, so vertical asymptotes and horizontal asymptotes are tied to limits involving infinity. Now let's talk about, given the equation of a function, how do you find horizontal and vertical asymptotes? By the way, I'm going to be posting the link to these filled in notes in your D2L classroom, so you'll be able to look at these at any time you want. All right, so example 1, to find vertical asymptotes algebraically. So to find vertical asymptotes algebraically, we're interested in where the limit from the left or the right for a particular x value equals infinity. And in the case where we have a rational function like this one, okay, we can set the denominator of a rational function. Sorry, I'm making a mess here. Hold on. Let me type this one. Okay, if you have a rational function, all you have to do is set the denominator equal to 0. And, well, assuming that the rational function is in simplified form, it's reduced completely. All you have to do is set the denominator equal to 0 and solve for x. Okay? So let's go ahead and look at g of x equals x minus 3 over x squared minus 4x plus 3. Again, we need to make sure that we have this in simplified form. Does this denominator factor? Can we reduce this at all? Does anyone know how x squared minus 4x plus 3 factors? Good. X minus 3 times x minus 1 is how it factors. So I'm going to think of this function g of x as x minus 3 over, and then we're going to have x minus 3 times x minus 1. Okay. So potentially we could have vertical asymptotes anywhere that the denominator is 0, but when you have a factor that's the same in the top and the bottom, that would reduce. What that tells you is that g of x is actually equal to 1 over x minus 1, except when x is 3, because when x is 3, this function would be undefined. But everywhere else, it's going to have the same graph as 1 over x minus 1. So as long as you have it completely reduced, all you need to do is to set the denominator x minus 1 equal to 0, and that tells you where your vertical asymptote will be. Okay, you might wonder what's happening at 3. 3 would be a hole in the graph, just a hole, not a big asymptote. All right, so in fact what this graph would look like, by the way, it's going to be the same as the graph of 1 over x, but shifted to the right 1 unit. You might recall that from the transformations section from algebra. So here's x equals 1, the vertical asymptote. It actually also has a horizontal asymptote at y equals 0. We'll talk about that, why that happens in a minute. And then it looks like this. This is what 1 over x minus 1 would look like. But it's undefined when x is 3. So there's actually a hole in the graph at 3. So it has one vertical asymptote and then a hole. Whatever factors cancel, that tells you that you have a hole, a little open dot in the graph. Okay, so now let's talk about using limits to describe the function's behavior at each asymptote. So there's one asymptote that I'm talking about, which is x equals 1. We'll worry about the horizontal asymptote later. We're just looking at vertical. All right, so what would be the limit as x approaches 1 from the left of g of x? So coming in toward x equals 1 from the left, you're following along this piece of the graph. What's happening to the y values? Anybody have any thoughts? What's happening to the y values as we approach x equals 1 from the left? So the graph is pointing downward, right? So the y values are becoming larger and larger, negative numbers. It's decreasing without bounds, so yes, so it would be negative infinity from the left. What about from the right? What's the limit as x approaches 1 from the right? So from the right, let me highlight that in green, going towards 1, we're going to have y values that are actually getting bigger, right? Without bounds. So that's going to be positive infinity, or you could just write infinity. So notice that at the x value where we have a vertical asymptote, as we said, you're going to have limits that end up being positive or negative infinity. Okay, now let's focus in. But the long and the short of it is, if it's a rational function, you'll just be able to set the denominator equal to 0, assuming that you've reduced, and you'll find any vertical asymptotes. And if you had some other kind of function, you would need to consider the limits as x approaches that number from the left or the right. Okay, now horizontal asymptotes, to find them is actually also pretty easy when you have rational functions, functions that are a ratio of 2 polynomials. So what's going to happen is, remember we said that horizontal asymptotes are the limit as x approaches infinity has to turn out to be some number L, and if that's the case, then you have a horizontal asymptote y equals L. And it doesn't matter if it's positive or negative infinity. So the interesting thing here is that as you plug in very large x values, these numbers on the end become insignificant. They contribute very, very, very little to the overall quotient. And actually, even these don't contribute that much either. Because of the fact that this highest power grows so much faster, like when you plug a 10 in, for example, 10 cubed is 1,000, whereas 10 squared is only 100, and there's nothing to plug in on this. So compared to 5,000, 401 is pretty small. If you plug in, say, x equals 1,000, you're going to get 5 billion on this first part of the calculation, and you're only going to get 2 million on the second part of the calculation, which is a very small part of 5 billion. So again, what we say is the highest power dominates. The highest power dominates. And so actually, the limit, this only works for limits to infinity. Let me be clear. But if you have the limit as x goes to infinity of f of x, that big function, it's going to actually always equal the limit as x goes to infinity of just the ratio of the highest degree terms. Okay, now, in this case, where the highest degree terms have the same degree, they cancel out. So you just are left with 5/4. The limit as x goes to infinity of a constant value is that constant value, 5/4. So that would tell you that you have an asymptote at y equals 5/4. So when you're looking for horizontal asymptotes, the y equals asymptotes, just take the limit to infinity and focus in on the highest degree terms. Now, you could have also found the limit as x goes to negative infinity, but notice that since the x values cancel out, it's not going to have any effect on the result. It would still be 5/4. Let's look at another example. Scenario 2, the highest degree terms are what we're going to focus in on. All right, so I'm actually going to find the limit as x goes to positive infinity of 3x to the 4th over 8x to the 6th. But when I do that, the x to the 4th cancels with the x to the 6th, and we're just left with 3 over 8x squared. All right, so what do you think is going to happen to this fraction as x gets very, very large? So if we plug in really, really large values, x equals 1,000,000, x equals 1,000,000,000, we're going to get itty bitty, teeny tiny little positive fractions. So this is actually going to approach 0. And the same thing, by the way, if we let x approach negative infinity, we're going to get itty-bitty tiny fractions that keep getting smaller and they approach 0. So when the degree of the denominator is 6 and the degree of the numerator is 4, something smaller, the limit goes to 0. That will always be the case. Okay, and then let's look at one more scenario, scenario 3. We have a higher degree in the numerator than in the denominator, which means the numerator grows very fast while the denominator is staying relatively small. So thinking of it as the limit as x goes to positive infinity. How did I get 0 was the question. Okay, so going back to scenario 2, how I got 0 is I could make a table of values, but I'm not going to. If you were to plug in larger and larger x values, the 3 stays small, but then the denominator is going to get to be really, 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 really big. The larger the x value, the bigger the denominator, and so you get a tiny little fraction very close to 0. And yes, 0 is the horizontal asymptote. Thank you for asking. So I should write y equals 0. That's your horizontal asymptote. Okay? All right, so the first scenario, we had the same degree in the top and the bottom for our highest degree term. They cancel out and we get our horizontal asymptote equal to the ratio of the coefficients. The second scenario, we have a higher degree in the denominator, and because the denominator is growing really fast and the numerator is staying the same, we get tiny fractions and the horizontal asymptote is y equals 0. Now, what do you think is going to happen in scenario 3 where we have a higher degree in the numerator than in the denominator? So what's going to happen is it's going to behave at the ends as we approach infinity. It's going to behave just like 2x to the 5th over 6x cubed. But we can cancel that, and this is the limit as x goes to infinity of 2x squared over 3. Well, what does 2x squared over 3 look like? That's a parabola, right? So what's happening as x goes to infinity is the parabola is going upward. And also if x goes to negative infinity, the parabola is going upward as well. So both the limit to positive and negative infinity is going to be positive infinity, which means that there is no horizontal asymptote. Okay, so whenever you have to find the horizontal asymptotes of rational functions, which are just one polynomial divided by another, you're going to look at the highest degree term in the top and the bottom. If they're equal, then the coefficients are the value of the asymptote, horizontal asymptote. If the denominator has a higher degree, then y equals 0 will always be the horizontal asymptote. Taylor's asking, wouldn't it be 1/3? Wouldn't what be 1/3? Oh, hold on. I'm sorry, I didn't mean to write 2/3. I meant to write 2/6. Is that what you're talking about? 2/6 of x squared or 1/3 of x squared, either way. Yeah, that was an error. Thank you. All right, and then if the higher degree is in the numerator, then you're going to get no horizontal asymptotes because it's going to act like the graph of a parabola or a cube function or something at the ends. All right, so in scenario 3, though, you're going to have to be careful and pay attention to what that end behavior would look like. It's going to depend on the degree and the sign of the degree of the x that you're left with and the sign of the coefficient, which in this case was positive. So, for example, on scenario 3 here, we had degree 2, which looks like a quadratic function. And it was a positive, so it opened upward. If this had been, say, negative 2/6 times x squared, it would have been a quadratic that opened downward, and we would have gotten negative infinity for that limit. You still would have no horizontal asymptote, though. But if I asked you for the limit, you would have to say negative infinity in that case. All right, so going to talk now about the end behavior and how it depends on the value of the coefficient and the degree of the x. All right, so anytime you're taking the limit of a polynomial or your rational function limit has simplified like it did in scenario 3 up here, you're going to have to keep in mind whether you have a positive or a negative coefficient and what the degree of the x is. So for example here, looking at this graph, I can tell you that it looks something like y equals maybe 5x to the 6th. Where am I getting that? Because this is clearly an even function because it goes up on both ends like x squared does. And it has a positive coefficient because it's pointing upward, it's opening upward. It could be 5x squared, it could be 10x to the 4th, any even power and positive coefficient. So in general, if you have x to an even power and you have a positive coefficient in front, then you're going to have something that has an end behavior where the limit as x goes to negative infinity of f of x is going to be positive infinity, right? So what this is saying is the end behavior on the left is going up, and the limit as x approaches positive infinity of f of x is also going to be positive infinity, meaning that it's going to go up on the right. So it's up on the left and up on the right. Okay, that's scenario 1. You have a positive coefficient and you have x to an even power. All right, in scenario 2, what do you think? What graph does this possibly remind you of? This one here in scenario 2. Maybe x cubed? So I know that this could be y equals x cubed, but since I don't know exactly the scale here, it could be anything with a positive coefficient and an odd power on the x is going to look just like that. It's going to go up on the right and it's going to go down on the left. Now, how do we describe that in terms of limits? So the limit as x approaches negative infinity on the left of f of x, whatever the function is, equals negative infinity. It's going down on the left, in other words. And then up on the right can be described in terms of limits as the limit as x goes to positive infinity of f of x is going to be positive infinity. All right, so that's scenario 2. So scenario 1, we had positive coefficient, even power on the x, and up to the left and up to the right. Scenario 2, we have a positive coefficient with an odd exponent on the x. It's going to go down on the left, and it's going to go up on the right. Oops. Okay, and then another scenario would be where it goes down on the left and down on the right. When would that happen? Would the coefficient be positive or negative in this case? That's right, it would be negative, like the graph of y equals negative x squared is upside down, right? So this is the case where we have y equals a negative coefficient times x to an even power, because they're both pointing the same direction. It's got an even power. So for this one, both the limits as x goes to positive and negative infinity of f of x are both negative infinity. It goes down on both sides. And then scenario 4, this is going to be a negative coefficient, but with an odd power. You can tell it's an odd power like x cubed because it's going up on one side and down on the other. It's going up to the left, though, and it's going down on the right. So instead of acting like x cubed, it's acting like negative x cubed. So you have a negative coefficient and x to an odd power. So whenever you have that, your limit as x goes to positive infinity of f of x means going to the right, that's going to be negative infinity. It's going down. And the limit as x goes to the left, negative infinity, is going to be positive infinity. It's going up. Okay, so if I were to give you polynomials and ask you to describe their end behavior, I would want you to pay attention to the highest degree term. So for example here, p of x equals 3x squared. The coefficient is positive and the x is being raised to an odd power. That means it's going to act just like y equals x cubed. It's going to go up to the right and down to the left. And I would expect you to know how to represent that with a limit. So you'd say the limit as x goes to negative infinity is negative infinity. The limit as x goes to positive infinity is positive infinity. On the other hand, in part B, we have negative 500x to the fourth is the highest degree term. So it's a negative with an even exponent, negative coefficient with x to an even power. That means it's going to look like the graph of y equals negative x squared. Which looks like what? A parabola going downward. So that means it's going to go down on the left and down on the right. If you can read that at all. Hold on. Okay, and we're going to have to stop there for today. Thank you very much for being here and for participating. Remember, the video version will be posted and you'll have a link to the notes as well. If this lesson was helpful to you, go ahead and give it a thumbs up in YouTube so other students can find it. And remember that although we don't have class until next Monday, that I'm still around in D2L via email. If you need to contact me, all my contact information is at the top of the syllabus in D2L. Have a great day, and I'll see you next Monday, and I'll hopefully hear from you during the week.